Variables aren't memory. Values live somewhere, and lifetime beats scope. So why do these bugs still ship in production systems written by experienced developers? Because the failures don't look like memory bugs. They look like timing issues, race conditions, random crashes, or it only happens sometimes. Let's walk through real failure patterns that only make sense once you think in memory and time, not syntax. Every failure case in this video can be diagnosed with two questions. Where does this value live, and how long is it allowed to exist? If you can't answer both confidently, the code is already risky. We're not comparing languages. We're not teaching syntax. We're tracing memory through time. This is one of the oldest bugs in systems programming. A function creates a value on the stack, then returns a reference or pointer to it. This is one of the oldest bugs in systems programming. A function creates a value on the stack, then returns a reference or pointer to it. The caller receives something that looks valid, but the stack frame is already gone. The memory may still contain the old bits until something else reuses it. The bug doesn't always crash immediately, which makes it dangerous. Why does this sometimes work? Because memory doesn't reset itself. The bits are still there, for now. The moment another function reuses that stack space, the value mutates under your feet. The system is consistent. Assumption about time is incorrect. Here's a more subtle failure. An object is allocated on the heap, but during construction, it escapes, registering a callback added to a list or shared globally. Other code now sees it before it's fully initialized. The memory exists, but the state is incomplete. The crash doesn't happen here. It happens later, far away. Scope didn't fail here. Visibility worked exactly as designed. Scope didn't fail here. Visibility worked exactly as designed. The failure happened because lifetime started before validity. Once memory is visible to the rest of the system, it must obey invariance. Construction is a dangerous time because memory exists before correctness. This one shows up in long-running systems. Memory is allocated once, reused many times, but not fully reset. A value from a previous request leaks into the next. Nothing crashes. The system behaves wrong. This is why memory bugs often appear as logic bugs. Memory didn't betray you. It did exactly what memory does. It kept its contents. If you don't explicitly initialize or reset state, all data stays alive. The CPU never assumes intent. It just reads what exists. Lifetime bugs cut both ways. Sometimes memory dies too early, like stack references. Sometimes it lives too long, like global caches that never reset. Both create failures. One crashes, the other corrupts behavior slowly. The common thread is mismatched assumptions about time. When debugging, stop reading code top-down. Trace memory instead. Where is it allocated? Who can see it? When is it destroyed? If those three moments aren't crystal clear, the bug is already present, even if it hasn't shown itself yet. Why do these bugs survive cleanups and rewrites? Because refactors change structure, not assumptions. If the mental model is wrong, prettier code just hides the problem better. Only a memory and time model exposes it. The stack isn't safer. The heap isn't dangerous. Each is corrected only when its lifetime matches the problem. Know what a variable means and ask how long memory lives. System becomes predictable, not simpler, but understandable. This is the difference between writing code and engineering behavior. Every system is a memory system evolving over time. if you design for lifetime first, scope, structure, and syntax fall into place.